So CCM stands for continuous conduction okay. So if you guys remember, we talked about synchronous and non-synchronous converter. So you have a PWM here, VSW. Load current, this is your inductor and this is your I load, and another structure can have okay. This is I load and this is your delta L. So let's say my zero current is here. This is 0 amp. Now if I keep reducing the I load, what would happen? So when will this valley point hit the 0 ampere? Delta L by 2. Okay. Now if I load is what would happen? Where will the value go? It will go to negative, huh? So 0 amp, it may look something like this. And if you have a 0, then it will cross at the midpoint. So which means, and if it's less than 0, let's say negative, so there is no issue, but it's a bidirectional. So if you operate this in CCM, okay, it doesn't matter what the load current is. So it will work for both negative and positive load current, even at a 0 load current. Okay, because this bottom switch will take care of that. But what would happen here? So this case is fine, straightforward. what would happen in this case? So, this is also okay. Okay, diode is not reverse biased, huh? So, this should be okay, huh? So, this now what would happen in this case? What would happen here? Will it go negative or not? It will not go negative because diode will turn off, it won't allow reverse current. So, your current will look like okay, and average of this would be your load current. Which means so if we compare this synchronous or non-synchronous, it's okay. So, this is your synchronous, this is your so the first thing is allows reverse current. So, inductor is always conducting. Okay. So, the current always flows no matter whether it is a reverse current or forward current, current will keep flowing. So, this does not allow reverse current. So, inductor does not conduct when I load is if I load is less than which one will have a better efficiency. If you look at here, you are dumping in the ground the current, okay, so that is lost, huh? So, in order to fill up that means you have to draw more charge from supply. Here you are not dumping any current, everything is supplied to the load. So, you do not need to cancel the losses. So, that will have better efficiency. Losses are more due to reverse conduction. Okay, which means better efficiency. What else? Okay. In terms of functionality, works for all load currents, which means positive and negative, works only for positive load currents, which means I load should be greater than 0. Okay. But in most of the cases, our requirement is positive load. We are drawing the current from the supply, we are not sourcing the current into the supply. So, non-synchronous is not a problem, but the problem is the diode drop. Okay. So, if somehow I make this diode with a 0 forward voltage, then I am happy. Then I would prefer this non-synchronous behavior rather than synchronous behavior. So, what we do actually, we implement some logic, and when the current crosses 0 or goes below 0, you turn off the bottom switch. The moment you turn off the bottom switch, it will behave like a diode, because it will not allow the reverse current, and which means you are able to implement an ideal diode with this switch with some extra logic. So, that will behave like a diode with a 0 forward voltage, because what you are looking, so you know, when the reverse current is there, this VSW node will go to positive. So, if the current is flowing in this direction, then it's this voltage is negative VSW. The moment current gets reversed, this will try to go positive. So, all you have to do, look at the 0 crossing point. So, when it goes from negative to positive, you turn off this MOSFET, and it will behave like an ideal diode, and that is what you do actually to enter this into a discontinuous. So, ideally, I mean, you would prefer this NMOS because of 0 forward bias, or you can say it is not 0 forward bias, but it is a IR drop. So, it depends on load, but if RDS on is very low, then it will be much low compared to your diode forward bias. Even if you use a Schottky diode, then you cannot achieve maybe better than 300 millivolt or so, but here you can achieve 100 millivolt or less, depending upon what RDS sound you choose. So, you have a flexibility of reducing that voltage. So, the conduction losses can be reduced by choosing this, but since this is a synchronous behavior, so you want a discontinuous behavior in order to save the losses or reduce the losses. So, we try to force this NMOS to behave like a diode when the current goes below 0. Okay. So, we will look at it how we do, but before that we need to go through some derivation. So, will this so you know the output is D times V in or VDD. So, if I stop the current, will still hold the same equation, D times VDD. Think about this. If you keep the same duty cycle in these two cases, so in this case, let us say you have some duty cycle, hypothetically assume, let us say 50%. Okay. Now, you reduce the load current. So, where the extra load current is going here, if this goes below 0, it is going into ground, correct. So, you can shift this waveform up or down based on the load, but here you do not have that flexibility. So, for the same duty cycle, the average current, which will have a more average current, left side or right side? Will have a more average current. So, now if you force the same duty cycle and your inductor is supplying more current than the load, what will happen to the output? it will start increasing. So, not what you need to do to reduce that again, you have to reduce the duty cycle. So, that means D into VDD is not hold true here. So, that is not valid at all actually in DCM. So, so this is the main thing you have to, which means we need to find what will be the V out here.